This is a video demo of the autonomous tourist robot. Designed and implemented by Ryan Neerman, Akshay Makin, Cheyenne Fan, Tom Haler, under the advising of Professor Natarajan. Our project sought to build and program an autonomous robot that would be capable of giving a tour of campus, thereby simulating a staff or student-guided tour. Some of the key features of our project include a graphic user interface, which offers two modes of user control. It also makes use of obstacle avoidance, which relies on the use of both a webcam and 3 sonar sensors. Furthermore, the robot comes equipped with a real-time map updating feature, which displays a map of campus and a red dot representing the robot's current position. Finally, the robot comes with an optional joystick offering 3 modes of user control. The general layout of our design is shown in the block diagram. The 3 sensors, the GPS, webcam, and wheel encoders, are interfaced with the netbook, which is connected directly to the joystick. The netbook is connected to the PIC18 via serial communication. The PIC18 is also connected to the sonar sensors and the PWM control, which drives the motors.
We have an Xbox controller with 3 modes: manual, autonomous, and semi-autonomous. The left button is used for manual control. The right and left joystick is used to control the right and left motor speed. Button A is used for autonomous mode and button B is used for semi-autonomous mode. The right button is used as the emergency kill button. This video demonstrates manual mode. The user has to press and hold the left button while controlling the right and left motor speed using the right and left analog sticks. This video demonstrates autonomous mode. The user has to press and hold the A button. The vision selects the best path and will control the left and right motor speed based on the curvature. This video demonstrates semi-autonomous mode. The user has to press and hold the B button while the vision controls the path. The user can control the motor speed using the left analog stick.
Our robot also contains a graphic user interface with 2 levels of mode selection. The first is a full tour, which will begin and end at the field house. The second is a user-defined tour, in which the user is prompted to enter the building that they would like to travel to next. Additionally, our robot contains a voice component, which plays pre-recorded descriptions of the buildings upon arrival. This video shows the option A selection for the GUI, which gives the user a complete tour starting at the most recent building checkpoint. This video shows the option B selection, which provides the user with a list of buildings for the user to choose from. It will start with the most recent buildings checkpoint and then prompt the user for a code name corresponding to one of the remaining buildings. This video demonstrates option C, which shows the brief concluding message and then loops back to the welcome screen to start the next tour.
In the vision subsystem, the program will generate 11 masks for path selection. First, the path that the robot needs to finish in the real world will be determined. Then the curvature of the path will be calculated. After that, projective geometry is used to map the real-world path into the image world. Finally, OpenCV library is used to generate the 11 masks. After the 11 masks are generated, they will be applied to the real-time video feed from the camera. The 11 corresponding indices will be calculated, indicating which path contains few obstacles. After a bubble sort, The medium index will be used as the threshold for selecting best path. The last step of the vision subsystem is to select the best path. The program will first go through all the indices left and select masks that have indices above threshold to make sure the robot stays on the pavement. Then the code will compare the mask heading with the current robot heading from the wheel encoder. The mask that minimizes the turning angle will be chosen as the best path. Finally, the speeds for the two wheels will be calculated based on the associated curvature. In this video, the top left is showing the real-time video feed. The top right is showing the processed image based on the threshold. The bottom left is showing the 11 calculated indices, and the bottom right is showing the best path selection.
The wheel encoders are used to help the robot navigate from one building to the next. The encoders provide a raw data value in counts, which is converted to counts per revolution and finally counts per meter. Once the data from the encoders has been converted to counts per meter, the distance is then converted to GPS coordinates, which provide the robot with its current latitude and longitude. Additionally, the encoders can use this data to give the robot its current bearing and heading. The image provides a representation of this where delta L represents the change in distance for the left wheel, delta R represents the change in distance for the right wheel, and delta theta represents the change in the angle. W stands for the robot's width. Finally, it is important to note that the wheel encoders can quickly accumulate error. The following image displays the encoder data outputs to a terminal screen. The GPS receiver will receive the RMC data. It will receive an A for valid data or V for invalid data. Once it's confirmed that the RMC data is valid, it will be sent through a parser function, which will tokenize the data into latitude, longitude, course or heading, the checksum, etc. That then can be stored into a structure. Once the data is stored in a structure, it will enter a callback function, which continuously gets the data from the GPS at 10 Hz or 10 times a second, and then it will display the map by entering the show map function. The GPS is used to display the map of campus. First, the program gets the coordinates from the GPS, then it fetches the map. Once the map is downloaded, the program uses OpenCV to display the map and the robot's current location, which is represented by the red dot. This video demonstrates the show map feature of the robot. The red dot represents the robot's current location and updates as the robot navigates from one building to the next.
The sonar sensors are implemented for obstacle avoidance. The side sensors are angled at 30-degree angles to prevent erroneous data readings. Emergency stop is implemented when the middle sonar sensor detects an object within 1.2 meters. This video demonstrates the flag being set for the sonar sensors. The flag is set when the object is within 1.2 meters of the robot. Once the object is moved out of the way, the sonar flag resets and the robot starts to move. When the object jumps back in within the 1.2 meters defined sonar sensor range, the flag is set and the motor stops. One of our major requirements was to get a bidirectional motor control system. This was achieved using two single-pole double-throw relays for each motor. These relays are operated by a source of 12 volts. At any instant, the current flows only in one direction. As the figure shows, the lower terminal of the motor is positive. The current flows from the lower terminal through the motor into the MOSFET, which controls the load current. When the relay switches, the current will flow in opposite direction. This video demonstrates manual mode. The user has to press and hold the left button while controlling the right and left motor speed using the right and left analog sticks. The video demonstration is a small tour from the Social Science Building to the Science Learning and Research Center. Along the way, it will avoid one obstacle, and at the end of the tour, it will play a small pre-recorded building description.
This building is the Science Learning and Research Center, also known as the SLRC. This building contains several science classrooms and labs, including one for molecular biology and one for biochemistry. Most of the classrooms and labs are on the first and second floor, while the observatory is on the third floor.
This final video demonstrates a tour from the Michigan Library to the IAVS building.
We would like to thank Professor Natarajan and Professor Miller for providing us with numerous tutorials, parts, and guidance during the project's development. We would also like to thank the members of the Intelligent Systems Club for assisting us during implementation problems and for providing us with numerous parts which helped to minimize our project cost. Additionally, we would like to thank Jesse and Ron for their willingness to provide electronic components and insight into how to wire and build certain aspects of our project. Finally, we would like to thank Steve Haler and Chuck Stockwell for providing numerous parts and tools necessary to build the robot structure. They were also very helpful in troubleshooting various problems with the motor control.